My name is David Hung, and then I'm very glad to be able to share some of the work that I have done, also in the area of atomization and spray. So again, having heard from Dr. Finotello's talk, that actually put together some of this, it's kind of like a double-header work on spray. So I guess I met her when we both attended a spray conference in Lund University last September, and that's why we are able to team up together again and to do this work. Again, thank you, Professor Yao, for inviting me, and I hope I will be able to share some of this work, to the community who are very focused on multi-phase flow. Before I begin, do you see a slide that is the entire screen, right? Not the presentation mode, right?
Yeah, it's
Good,
clearly
perfect.
visible.
Okay.
Yeah, perfect.
Again, this is the beautiful city of Shanghai, and then I would like to invite those who might be in Shanghai or coming to Shanghai come to visit at Shanghai Jiao Tong University. So today, my idea to share with you is something that I have done for quite some time, looking at fuel spray that is used for internal combustion engine. But the fuel is very, large in terms of composition. So we are trying to use something what we call a surrogate fuel, which is to mimic a regular fuel. But to do that, we are particularly looking at how machine learning framework can be used to do prediction. So to put the context together, I would like to talk about a little bit about machine learning application for spray. I'm sure many of you have done some similar work for other multi-phase flow. To put into the context for spray, I think I would like to share some of the work that has been developed in this domain. And because it's touching on fuel spray, so the concept of flash boiling spray is very useful in this discussion, especially how that is applied to the internal combustion engine. And then I would point out a specific example that I have done myself, applying machine learning techniques to predict this type of flash boiling behavior. And then I would like to conclude with some thing that I think would be worthwhile for us to look into as future work. Before I begin, I would like to always start with the team. Team means together everyone can achieve more. Indeed, the work that I'm presenting is a lot of hard work by our colleagues at Shanghai Jiao Tong University, Professor Yang Che, Professor Ming Su, and Professor Sheshong Li. And then we also have a lot of very capable and smart students who have helped us work with us along the way. And we have a number of students who graduated who work on this topic. And I'm also fortunate to have quite a lot of young graduate students to work with me, and also a team of undergraduate students from all over the world. A little bit background about myself. I've been working at Shanghai Jiao Tong for the last 16 years. Currently, I'm John Wu and James Sun Chair Professor in Mechanical Engineering at the Global College. I've received my PhD from Carnegie Mellon University in the United States. And my interest has mostly been on fuel spray, spray cooling, medical spray, and also lately into diagnostics using tomographic imaging techniques, laser-based diagnostic techniques. And I'm also a editor-in-chief for Asia for our journal, Atomization and Spray. As a matter of fact, this is the journal I'm sure Dr. Finotino is very familiar with. And this picture was actually taken at ILA's Europe meeting in Lund last year. And I'm joined by my colleagues, Professor Marcus Herman, who's the editor-in-chief in Americas at Arizona State, and also Professor Gunther Brunn, editor-in-chief in Europe from GRAS Institute of Technology, and also myself from Asia. So if you're interested to publish work specifically for this type of area, atomization and spray droplet, please consider us as your primary channel for publication. So with that, I would like to start with this paper that I have read and I found very exciting. This is a new journal called AI Thermal Fluid. Again, some of you know Professor Makidis from Imperial College. And this is a new journal focusing on AI and fluid. And since we are doing multi-phase flow, I thought this is quite relevant to what we do. There are two lines here, right? If you think about using Scopus search, just type the keyword thermal, heat, and fluid, which is very relevant to what we do. The green line shows the publications for the last 4 decades or 5 decades, starting with about 10,000 publications, gradually increasing at about 7% per annual rate, and right about 100,000 right now in this time frame, which is very regular and very expected as we have done this for the last many years. Now, if you add the word artificial intelligence or machine learning or AI into the search, together with thermal, heat, and fluid. You can see that back in the same time frame, we only had about maybe 10 papers in the 1970s. And that the number of paper gradually increases like in the other spectrum. But all of a sudden, in the year of 2018, 1920, and to the last few years, the number of papers published with these keywords in have expanded exponentially in very, very high steep rate at a 60% rate. So that has told us something that I think if we are handling the area of thermal fluid, especially if you're interested in AI technologies or AI techniques, I think there's a huge interest from all communities. So I would challenge all of us, including myself and my student, to be able to understand the different use of AI tools and how they can actually enhance or assist our work in research, but not losing the focus on the primary is to really get the basic problem of what we're trying to solve, and also get to the bottom line of the core data, which I think I'm particularly interested in. So you can see that the increased rate is something that I think everybody should pay attention to when it comes to the use of AI tools in scientific work. So here are two images that I showed. On the right, you can see that it's a very typical droplet impact on a surface. And you can see that two examples, right? So on the right, you can see a drop impact, and then it grows, and then you can see the recoil film because of viscosity, and then you can see a thicker film rim coming back, and then this is part of that impact process. I have a similar video on the right where, again, the drop impact on the flat surface, and it becomes a crown, and then because it's a top view, you can see the development of the maximum spread diameter, and then the rim, the fingers, and very familiar with. So you can see that, it's a very typical pictures. Of course, in this context, you can see that there are some very subtle differences. Even though they show similar process, but I'm sure in the context of what I would carry on, you expect one is actually a ground truth by actual recording of the experiments. One is actually built by machine learning code. I would like to see which one do you think is the actual measurement of so-called the ground truth, and which one might be the one generated by AI tools. Let me play that again. On the right, you can see that this is the development of a high-speed video recording at about 2,000 frames per second. And then on the left again, you can something so very similar. Okay, but you can probably start to see some subtleties. And then to tell you the truth, actually, the right is the ground truth, actually taken by high-speed video at 2,000 frames per second. And obviously on the left, this is a what we call fake or predicted video using what we call a pick-to-pick machine learning algorithm. Of course, the title today is not to look into the why they are like that, but you can see that there are a lot of similarities and a lot of things that potentially we can explore using machine learning techniques, perhaps can predict something that we have never done. Many of you have experience. I would like to probably take that opportunity for us to discuss on that further. So just a very typical overview, and if you have done machine learning, AI, MI, ML, deep learning, and then you probably have seen these terms quite regularly. And I would like to put that into the context of fluid mechanics, and more specifically to atomization and spray. So you can see we have divided that into supervised, unsupervised, or semi-supervised. And definitely there are different techniques or different ways that you can use these techniques for. Again, for fluid mechanics, AI, I think, can help us do a few things. Maybe we can use it to predict the trend, discover some pattern that we have not been able to identify, accelerate the simulation that we have taken too long, or maybe doing some governing equations deviation that we can use data as the part to direct to do that. So in that context, maybe supervised learning can, maybe we can call it as learn from our labels, because you predict a certain part of the behavior. In this case, actually the spray collapse from this work. If you don't want to label anything, you want to just use the tools to find some hidden structure in unlabeled data. For example, clustering of a vortex pattern from a flow would be a perfect example for that. If you have semi-experience, learn from experience, and maybe learn to optimize a certain signal, maybe a flow control or maybe adaptive mesh refinement from your experience, then we can probably lump that into what we call a semi-supervised learning. But in all respect, we must have good methodology. We must have good data that we can use to do this type of work. Apart from that, this graph actually shows that before you apply machine learning model, you must know exactly what you're trying to do. Are you trying to identify the feature, or do you want to separate zones or categorize things? So the feature section is critical. If we don't know exactly what we want to do, machine learning just create a lot of chaos. But if you know exactly how we want to use machine learning tools or models to do certain things, then I think that might be something worth to try. Again, artificial neural network depends on different layers. You have input layer, you have many hidden layers, and of course, you have output layers. So to put the context, we put the raw data into what we call a first layer into the ANN, right? This corresponds to many of the features in the input data that you want to use as a basis to analyze. The middle part obviously is the hidden layers. The more the layers that you have, the more complex the task that you are trying to do. Of course, it also has different type of weights and bias to relative to the input data. But the critical thing that we should focus on is very good at resolving nonlinearity. So something that has a huge gradient in terms of these features. The better the gradient, the more the gradient you have, the more nonlinearity you have, the more actually the network can actually do the work. And of course, finally, the final part is just the output. The number of neurons in the layer correspond to the classes in how you identify the problem, or the number of input and output that you have based on the regression problems. So again, in our context of spray, because we deal with spray images a lot, so the CNN or convolutional neural network is actually quite common in our domain. We apply the network to the input, and then we try to capture some of these features that we identify in our images. So again, if you have a specific set of images in what you do, consider CNN as a good tool that you can use to extract the features from the images. Another thing that we do a lot is because it's a spatial time temporal behavior, so things happen, change over time. So if you have that type of images or data, perhaps you consider recurrent neural network, RNN, because they have some of this process in the time domain. This loop actually allows information to persist across different time steps, especially if you have sequential data with temporal dependency. This type of network might do some good process for you. Now, let's come back to the spray. I'm, again, very grateful for Dr. Pinotello to tell you about all the spray. And then it's fascinating, in my opinion, because the liquid becomes so dispersed. Different liquid show different behavior. And this is just an example of the liquid coming from a nozzle. You can see a lot of things happening. You have bubble nucleation, you have primary breakup, you have secondary breakup. And you know what? If you want it to ignite in case of fuel, then it does. So the mixing between the liquid fuel and the air creates a lot of challenges. To put it this way, if you look into the spray, there are a lot of things that we are studying. The drop size, the velocity, the spray pattern at different location, and then whether they are primary breakup or secondary breakup. And if you use different liquid like molten metal, it's very challenging. If you use fuel spray, you have to consider evaporation. If you look into something more exotic, you have to consider non-Newtonian breakup. So I think this is quite exciting in my domain. So to be able to do that, again, let me just put this slide as a summary. Again, if you're interested in spray and atomization and applying with machine learning tools, maybe you are thinking about droplet sizing, velocity measurement, or identifying spray boundaries. So if you have that request, then mostly you are doing image-based analysis. Maybe you are doing PLIF, PIV, high-speed video. Then what I mentioned about CNN, UNet, or YOLO might be a good primary algorithm to use. If you're thinking about doing some fast, accurate model predicting the spray characteristic from the sorted mean diameter, prediction like that, so predictive modeling and surrogates, the data can be from your experiments, from your CFD simulation. So DNN Gaussian process regression or random forest, these are perfect tools that you might want to consider. Again, if you want to design a design space, right? Design a nozzle geometry to find the optimal breakup configuration for your spray. So it looks like you might have a design optimization problem. The data could come from your parameters or performance metrics from experiments. So the genetic algorithms, the Bayesian optimization could be perfect. You want to find out some hidden relationship from your closure model, from your CFD, or maybe from your empirical models. That seems to be like uncovering the physics. And then you need definitely high fidelity simulation or data. Then the physics-involved neural network or the PIN network or this symbolic regression could be good tools. Last but not least, I do a lot of pattern identification. I identify pattern from different spray conditions. So I have a classification problem, clustering them, putting ID to them. So the data could be from images or could be from sensor data. So the k-means, the self-organizing map, the SOM, this could be quite exciting and useful. So in summary, again, the speed, accuracy, automation, optimization are definitely key advantages of applying machine learning in spray research. Of course, some of these reasons are very well studied, but in the next half an hour or so, I'll give you an example. And at the end, I would also like to point out what are the challenges that we need to focus on, because these things, if driven, if operated correctly, can benefit a lot of our work. But if they are not treated correctly or with careful determination, they could actually come back and haunt us. So with that, I'd like to point out why we are doing that, because I'm an engine guy. I have worked on fuel spray a lot. And right now in China, most of these vehicles are EV, as you know, but in Europe, in US, fuel-based vehicles are still quite dominant in most of the sectors. So my interest is to make sure that we can burn fuel in a more efficient way with less emission. So one technology is what we call the gasoline direct injection, which is something that is exciting, has been applied to the vehicle for the last 20 years. And you can find a lot of vehicles that are applying this technology into the fuel system. So the primary purpose is to make sure that we have good atomization, good mixing, good fuel mixture preparation. And then when it combusts, it would give you fuel saving, emission reduction, and efficiency improvement. However, things are happening in the engine for obvious reasons. One special issue is when the fuel, if it's not mixed well, but if impinges on the cylinder wall, it is definitely a challenge, because the impingement would cause a lot of unburned fuel that would ultimately becoming soot. That is one problem. Second of all, you feel like the fuel spray is injected through the injector into the cylinder. Well, yes, you're right. This is a picture of the injector tip. You can see that there are 7 holes clearly when the injector is new. But after a while of engine operation in a very hostile environment, the heat, the mixing, the residual fuel, everything would clog up the injector tip. You can see that on the right, injector tip, I don't think we can even identify where the holes are. If they are there, they could be partially blocked, completely blocked, or they could not be fully functional. That means the fuel spray coming out from an ideal condition is quite different than after the vehicle has used this injector for, let's say, 10,000 kilometers. With that, you can see that we can have well-burned combustion characteristic, we can have a partial burn, or we can even have misfire, no combustion cycles. So things happen for obviously that this is a very challenging, and it takes many people to come up with different solutions. But one of the things that we could look at is fuel, right? Maybe if fuel is the primary cause of this type of plugging, so we have to probably do something to that. So if we put into the perspective of the injection system that we have nowadays for gasoline, whether the fuel is injected into the port of the intake port, called the port fuel injection on the left, or the fuel spray is directly injected into the cylinder, called the GDI or SIDI, where the mixing is happening in the cylinder. We do have always an interesting situation that we want to study how good the mixing is. So I showed you 2 images. The left video is a combustion of a diesel engine, which is very common. You can see that the mixing injection happens in the cylinder, right? And then the flame starts from the tip of the cylinder wall where the mixture homogeneity is right for combustion. And on the right, this is a typical example of a spark ignition engine. You can see that the flame starts at the spark plug and the flame propagates for the cylinder. So the propagation obviously depends on how good the mixture is. So with these ideas in mind, so at SJTU, we do a lot of research. And again, for those of you who might be doing engine research or might have an opportunity to come to Shanghai Jiao, I would like to tell you that we have a lot of hardware diagnostics that we deal with this type of engine research. First, we can look at fuel, look at spray, liquid spray versus flash boiling spray. We can look into different measurement of the spray, the flow field, evaporation, drop size, and emission from our measurement standpoint. And we also have fuel air mixture and also validation using CAE, something similar to what Dr. Vinotello just presented in terms of modeling. And last but not least, we have a lot of engine combustion capabilities. We want to make sure that the fuel that we inject into the engine, the combustion, the post-combustion in terms of engine knock, pre-ignition are all being studied. So here is a typical example pressure curve that you might see in a cylinder. Now, to put a perspective, this is the piston at the top dead center at 360 degree, and then the piston moved down to the bottom dead center at 180, and then again the piston moved back to the top. So this is a half the cycle of an injection. Well, you can take a look. The fuel spray at the early intake condition looks something like that, but as the in-cylinder increases in pressure, so obviously the spray is becoming a little bit smaller and more compact. As in the last phase, before combustion occurs, the spray is even more compact. So at the change of in-cylinder pressure, which also results in higher temperature, the spray changes a lot. So this is just a very typical phenomenon in internal combustion engines. Not to mention if you change the fuel type, whether you are using gasoline or using an ethanol, the spray also changes quite significantly. So it takes a lot of understanding between the condition of the spray exposed in and also the type of fuel that we are testing. Another situation of worth interesting is what we call a superheated spray, or what we call the flash boiling spray. Now you can see that this is a three-phase the two-phase diagram, P and T diagram, for whether you have a solid phase, a gaseous phase, or liquid phase. And you can see that if we are talking about injection of liquid, so we are injecting from a high injection pressure to a lower injection pressure at the liquid phase. So that looks something like that. So you can see that this is a breakup, and this is a typical fuel spray that is typically in liquid phase. But if you move to a certain point towards away from that temperature, let's say to here, then the injected initial part is liquid at the ambient phase, but in the initial injection position is already superheated. You can see that the tip of the spray obviously is very different. And then when it injected into the atmosphere, which is already in a flash boiling condition, then the spray is collapsed, very compact into the center part and very dense in the middle as well. The same injector spray exposed to different ambient temperature and pressure condition can exhibit something like that dramatically. So how do we define that? Well, we use the temperature difference between the fuel temperature and the boiling fuel temperature of that particular ambient pressure as one way to do that. Or you can use a ratio of a separation pressure at the fuel temperature and then compare that with the ambient pressure. So regardless of what you do, you see a very nice collapse of a line in terms of the properties. So we use what we call a superheated index, SD, to define whether the state is in liquid state, in flash boiling state, or in the middle between a transition. So this is how we use this type of terminology to look into the fuel spray. So with that, you can see that the spray can be very different in structure. Liquid is very clear from multi-hole injection, or is collapsed when you have a flash boiling condition. You can also see that the pattern is different. This is a pattern of the laser sheet pattern and the cross pattern. Obviously this is an 8-hole injector, so there are 8 different plumes discretely separated from each other. But if it's under the fresh boiling condition, it could collapse into one big plume. And of course, that would affect a lot of other things like initial formation. This is the initial hole formation, whether you have a liquid spray versus a fresh boiling spray. And you can also look into, for example, the drop sizing. And obviously, the drop sizing reduces as you go from more liquid type to a fresh boiling type. And then the spray flow is also different. You can see a very discrete, separated liquid flow compared to when you have a collapsing fresh boiling spray. Everything collapses to the middle. And also, seriously, if you look into different condition, different fuel type, and different injection condition, you can have all sort of correlations, whether it's a penetration, the spray angle, or this drop sizing information. So we have done a lot of this type of work if you're interested to do that. So again, before I jump to the final part, these are the things that we're trying to do. Understanding the mechanism of fresh boiling spray, using measurement diagnostic to measure the data, and then trying to come up with different ways to predict whether it's a CFD-based tool or machine learning-based tool. So this is our focus. Again, you can see that we can use mist scattering to look at the pictures of the spray, use phase Doppler interferometry to look at the particle sizing information, using a 2-color PIV to look at the liquid phase versus the ambient phase, look at the velocity flow field among the 2 interactions. You can use liquid-induced fluorescence or exit-plex fluorescence to look into, again, liquid phase versus the vapor phase, and high-speed imaging, slurring imaging, or laser diffraction to look into the other part of the spray. We also have an interesting setup that we are using different cameras in a circular ring. Here is 2 pictures of aerosol that we generated from at 90-degree difference, and then we have 10 cameras surrounding this setup. And with 10 different cameras that we can actually reconstruct the spray or the aerosol image and to put into a 3-dimensional structure like what you have seen on the lower right side. And with that structure, you can do some slicing information, and you can compare that slicing information based on the 3D reconstruction compared to a mist scattering of the cross pattern. So we have work that published last year in Optics Letter. If you're interested in this type of technology for visualization of 3-dimensional structure, please let me know. We also have done a review paper in PACS, Progress in Energy and Combustion on Fresh Boiling, Atomization, and Combustion. Again, you're very welcome to take a look at this literature review. So in the final 10 minutes or so, I would like to talk about our work on fresh boiling spray using multi-component surrogate field. And the work was published in field and other conference as well. Now, with the background that you have seen from Dr. Finotello and myself, you can immediately identify that this is the spray pattern that we are seeing. So you have subcool liquid spray or flash boiling spray, and the bottom color pictures are different cross sections at different distance from the injector tip. You can see that clearly for liquid spray, 6 plumes are clearly present at a discrete distance from each other. As you're going from liquid to flash boiling, the spray plume collapse and form a very concentrated in the middle. So you can see immediately, wow, we have images. We have different type of images, and we also have different classification of images. So this data set is a perfect candidate for machine learning type of prediction application. Well, again, if you look into the further context, because we already talked about fresh boiling spray is a function of fuel temperature, fuel component, ambient pressure, right? And we also able to identify whether it's a collapse, not collapse, or transition. So it's a classification, it's an input problem, it's a CNN problem. Now, let's look into a further geometry. So our challenge is in an actual field, the field is very complicated, and we don't even know how many components are there. The spray geometry is highly dependent upon the fuel type that we have. The question now is, it's too complicated to do gasoline because there's so many components and it's so hard. If you only use single component, let's say heptane or pentane, it's too simple. It's not even representative of a regular gasoline. So what do? Well, we said, what about multi-component? Maybe a few single component fuel might do the job. So with that, we look into 4 parts. We look at evaporation, we have the spray behavior, the spray pattern, and particle size using the techniques that I just introduced to you. Looks like if we are doing that, we should be able to identify a combination of this type of single component fuel that can be used to mimic gasoline. As a matter of fact, we did that, and it turned out to be quite okay. So this slide shows you a 3 different surrogate. We call it the light, the heavy, the middle, and then the inverted triangular is the gasoline. So we're able to use this type of composition between heptane, octane, and decane to mimic the gasoline fuel to the context of distillation. So you can see that the curve represents different part of evaporate or distillation based on the volume. So we have a good formula, this type of fuels. So with that, we look into a triangular methodology. So this is a triangular map, shows different component of decane, octane, and pentane. So you can see that the 3 propositions that we study are all within this domain. Great. Now, so we have this type of 3 components or 3 surrogate. Then if you are able to do imaging work, you can start doing right now. We also identify the single point, which is a 3 single component. For example, if you look into this point here, this means it's 100% isooctane. Look at the lower left one, which is 100% N-decane, and look at the one on the lower right, which is 100% pentane. So we have good fuel, single component fuel and multi-component surrogate fuel. So we can look at anything on the line, which is a 2 component. So 3 component within the region, 2 component along the line, single component on the 3 vertices, ready to rock and roll. So here is the first picture. So this is the point where we look at the vertex, there's 3 single component fuel. Now, if it's a liquid, they don't show too much difference as expected because all of them are liquid. And if you look into the 3 combinations within the 3 surrogate fuel, they also show very similar work because they're all liquid. As we move from liquid fuel to a transition, look, something is happening. Well, the liquid remains quite liquid if it has more heavy component, like decane or isooctane. On the right, if you remember, this is the case where we have lighter component of N-heptane, and it's easier to flash boil at condition. So you can see a slightly change of the spray pattern. Look into further, other things doesn't change a lot. But if you look into superheated condition, where is the red square, you can see that for the case where you have heavy component of decane and isooctane, doesn't change a lot. But if you have a component where you have a heavy presence of pentane, that drive evaporation, that also changes the shape a lot. So now we understand a different combination, the fuel spray is different. So we have a 6 component here. Can we do more work? So let's say systematically, we break this region into 15 different mixture formations. You have a lot of single component, which is at the vertices. You have quite a few of 2 component, which is in the middle or along the line. Or you can also certainly pick a lot of the points within that free zone, which shows you different combinations. So we are increasing from 6 mixture formation to 15. So of course, we did a lot of work testing using imaging technique. And here is the spray pattern that you can see. Obviously, you have here on the lower right side, when you have more presence of N-heptane, at fresh boiling condition, you can see spray collapse. On the contrast, if you have less of that component, but more of the isooctane or decane, even though at very likely condition for temperature higher or increase in pressure, the spray doesn't collapse or remain in very liquid state. So this is the trend that we see. And then the question now is, can we map out which zone is subcooled, which zone is fresh boiling, and which zone is fresh boiling? Can we also predict the spray behavior under the untested condition? Well, traditionally, you would do a lot of tests. right? Identify different components and then start to do the test and then do that. That's one approach which I think is still very useful. But can we predict something in the middle? If I tell you any single component composition, can you at least predict whether it's going to be fresh boiling, non-fresh boiling, or transition? I get the answer is yes, based on whether they collapse from the tested point, and then based on the cross pattern that we predict, should be able to do that. So we experimentally investigate this behavior as what we have presented, and then we start to look into machine learning based on the type of things that we want to predict. Then we have limitation in time measuring the spray. We also have limitation in the quality of the data. So perfect. We are able, or at least we want to predict the spray behavior under the condition that we never tested. To do that, we have to identify the key input, which is the superheated component. For single component, it's easy, but for multi-component field, we identify a ratio of K1 over K2, which is already identified in popular literature to identify the superheated behavior if you have more than one component. So with this, we have done a lot of our data. We can see that we identify different data input as non-collapse, transition, or collapse state. And then we also use a typical machine learning classification or way to input our data. And then first is to classify. It's a machine learning network that allows us to classify, which is a residual network, a supervised learning network. And then we fit that into another network, which is called decision tree classifier, and which is we identify fuel temperature, ambient pressure, and component as the input. And then we use classification and also the visual network to combine into forming this type of map. So this map now identifies which zone is going to be non-collapse, which zone is semi-collapse or transition, which zone is going to be collapse. So now it's very useful because if you want to change a different condition, let's say from 50 kPa to 20 kPa, now you can see how the zone changes from one condition to another condition. Some actually get smaller. Or in other words, if you are changing the ambient pressure from 50K to 20K, you are enlarging where the fuel spray would collapse. You would expect to see a lot more fresh boiling spray. Of course, sometimes there's mismatch. For example, in this case, we expect it to be transition, but it turned out to be non-collapse, which is something that we expect because it's the plume structure that actually confuses the code, how that can be classified. So with that, the next question is, can you actually predict the pattern? Now, we know the zone that we can identify, but can you predict what it actually looks like? It sounds like a very perfect example for machine learning application. So we propose a deep learning framework to actually predict the spray pattern based on the range. Well, obviously, you have to start from something. So we start from a case where we fix a certain component, let's say A and E, and we use C to do interpolation to predict what that might be. Or you can do extrapolation where you would have 4 cases in a sequential way and predict the last one. Whether it's interpolated or extrapolated, you would have to do a network like this. In the interest of time, let me skip that a little bit. So you can see that at the end, after you input the raw images, you can have a label, which is a ground truth, or an output, which is a predicted one. Likewise, you can do a similar work for extrapolation. So to make the story short, so here is what we are experiencing. So we fix octane, and this is what the prediction looks like, different combination. We fix decane, this is what it looks like. And if we fix pentane, looks like the prediction is similar. All of them show very similar prediction, but as a matter of fact, the accuracy for higher pentane change when we fix octane seems to be more accurate in terms of prediction. Where if you fix the pentane and maintain vary the octane and decane, the prediction accuracy is lower. It actually turns out that for machine learning, we talk about highly nonlinear in the layers. if you have a lot of gradient over your data, it's actually better for the machine learning tools to do the prediction rather than if there's no change, sudden change. So this is quite an interesting fact. I think if you are interested in that, we can share that more. So in summary, I think the future directions for our work in terms of spray and atomization, and specifically using machine learning to do more or maybe to be able to predict is quite promising. At least the work that we have done shows that type of promises. But there are also challenges because if you don't have good data, if your model is not well studied, if your physics is not consistent, or if you do not have the right amount of computational resources, or if your features that you identify is not really certain, these are the likely challenges that we might see when it comes to final prediction using machine learning code. So again, if you're interested, I would be able to share some of this work. Some of these are our own work. Some of these are the work that are from the community where people are doing a lot of machine learning and in the context of spray atomization. I want to show this at last picture. I think I like it because I think we have graduated and we have wondered what will hold our future. I think the future might be AI. But before we go into that final picture, I think we want to make sure that there must be also human intelligence. So whatever we are doing, whether it's a spray or two-phase flow or something that we are excited about, if you are doing AI, definitely add our own human intelligence with that is something that I think the ultimate approach to solve most of the research field problems. With that, again, I thank you so much for your time. And then I want to acknowledge, again, some of the work that we performed here at Shanghai Jiao University, some of our previous collaborators in the automotive sector, and also from Oxford, where we have received funding to do some of this work and so forth. And then if you have a chance to come to Shanghai, I welcome you to come to Shanghai Jiao University, to Global College, and then we will have an opportunity to discuss further to the context that we are both excited about. With that, thank you so much.
Thank you very much, Professor Hung. And luckily you're still here, so we can also discuss now, which is great, of course. So yeah, it was a very interesting talk. I already got a few questions in the chat, and I'll start from the last one. Professor Jiao Yun is asking, for your case study, do you consider phase transfer during the spraying process?
The phase transfer do you mean the phase transfer from liquid phase to gaseous phase?
I suppose so. Yeah.
Okay. Well, maybe let me show that context again, right? Actually, the context. Sorry, So let me just go back up a little bit. Sorry, it's a little bit slow doing this way. Let me explain first and then come back to the context. Well, when we inject the liquid into a chamber, for example, right? The chamber could be atmospheric condition. Like, for example, you look at these pictures, right? It's a liquid injecting into an ambient condition. If the condition is all just ambient, the liquid is remain in the liquid phase. And then, but if you are increasing either the temperature or reducing the ambient pressure, it creates a condition where the liquid can go over phase change, right? So that's exactly what the condition that we want to understand and predict. So in the liquid phase, when we call non-collapse, it's all liquid phase. At the state where it's collapsed, we believe that is a flash boiling behavior that's happening because at the same time, it's also had a higher temperature or lower ambient pressure. So it might also exhibit some evaporation on a certain component as well. So without going into deeper into that discussion, the state that we inject into the condition is exactly where they show up as in the condition. I hope that answers the questions.
Yeah. Well, we can ask Professor Jiao Yun, who asked the question. So I would also like to give him the floor for another question, which maybe you can ask that one about that AI is believed to create 1 to 100. Maybe Jiao Yun, can I give you the floor?
You're asking me?
Professor Jiao, hi, how are you? Good.
Yeah. Uh, yeah, David, thank you very much for your presentation. Actually, I feel very excited and also feel very boring. Yes, of your futures. Yeah, you know, AI actually are very strong actually from your work. Yes, I already seen it very strong tool to solve the many problems. And just now you also the last page you also give some challenge of work in the futures.
Yep.
So yes, as I am to show the questions and you know I just for the for the flow dynamics I don't know it's a very long time research in these areas but presently you're using the AI and help us to to go ahead. So this is my wondering in the futures the medicines will be done by AI and it's possible with you give us some suggestions or some some the bright futures using the AI to solve many difficult or very challenging work in the futures. So I just like to know about your thinking about this. Yes.
It's a very good question. I think I would probably point out to this slide here. Some of these names are very well known in the field, right? For example, I'm sure many of you have read Professor George Kanedikis' work on in science, right? You know how hidden flow structures can be resolved using Navier-Stokes equation in a machine learning form. I think it's exciting, but I also would be cautious because AI is not for everything, but AI is for something that if you can identify the how AI is developed or the particular algorithm is developed with the particular applications that you want. In my case, I do a lot of imaging, right? So when you deal with flow patterns imaging, nothing stand out from identifying what the features are, the vortexes that are happening in a flow field. This change of the shape of the streamline, or like I mentioned, the collapse state of a fuel spray, right? If you have that type of applications in mind, and then CNN seems to be a perfect network for that. But with the network, you have to also train it. If you have very limited data, it's impossible that you're going to train the network to be well performing to what you want. You cannot overtrain it and you cannot undertrain it. So I think the understanding part is you train it and it seems to be well working for what you want, but can we then add our intelligence by our researchers' mindset to interpret what is predicted? So that's why in the last slide, I think I'm very encouraged by seeing what we have done. At the same time, I'm also cautioning myself and my student that without human intelligence, everything comes up could be also a big black box. So I guess my encouragement to all of you who are doing this type of work is looking to these particular challenges that has been published in this paper. I think they are very well spoken of in terms of different part, whether you have good data, you have good model, your consistency in terms of your constraints, and how do you compute the computational complexity and what are the exact thing you want to resolve, with the future work that you're doing. So it's something that I think we all would work together, in the future.
Thanks.
Yes, thank you. Yes.
Yep.
Yeah, it's very good. Yeah, actually. Yeah. Thank
Yep.
you.
Maybe I can build on this. So one question asked is in the chat was which physical laws are integrated into this deep learning model? And before you answer, maybe we can also turn the question around. So here the question is, what physics is being used in the deep learning? But maybe we can also use deep learning to find new physics.
Yeah.
What are your thoughts on this?
Yeah, thank you very much. But it's a good question. We can show you what that network is, right? So maybe let me see what would be the good way to start it. Now, let's look at this one here, right? Well, if you think about it, this is a supervised learning. What it means is, you label what it is, right? Now, so the machine learning code doesn't label it for you, for me. I label it myself. The physics is not happening in the machine learning code for this particular application. the machine learning code actually is happening to identify how these images of labeled data can be looked into different layers by identifying the features that we tell is collapsed. So in other words, if you look into this particular classification code, it's all about telling the code what to do when you have identified or labeled data. That's one thing. Now, if you look into the second part, which is a decision tree, okay. Now, the decision tree come with this type of modified setup. If you remember that the physics of superheated degree boils down to the pressure ratio between the saturation pressure and the pressure of the ambient condition, right? And then you also remember that I talk about particular things, that this K1 and K2 is where physically they are, studied and so forth. So again, the physics happening in this model is when you apply that into the modified superheated degree. That's the physics part of it. So I'm not sure if I answered that to the context, but in some cases, machine learning tool is not to resolve the physics, but you have to identify the physics first, and then use that to put into the context where the code or whatever algorithm you're using reflects to the next step that it should take from the physics. So perfect example is this. If I blindly, without labeling, to tell my code, okay, identify what they are. Now, this is maybe a Gen AI or generative AI technique that we are doing, which is different than a traditional AI, where the model has to be there, the data has to be there, and then the algorithm has to be rigorous in some cases. I hope I answered that question, but in this particular work, it's not the physics.
It's a very complicated thing, and there's a lot of different forms of machine learning, a lot of different forms of AI, and you easily get a misunderstanding of what somebody means. So you definitely answered my question, but allow me to also share a bit of my own thoughts on this one.
Yes, please.
So let's say if we go back 100 years ago, we did not have computers yet, but there were a lot of our former colleagues, so at the time, our fellow scientists, who were doing a lot of interesting research and also developing new insights, trying to figure out new physical phenomena, trying to understand things. And what I think they did was, use their eyes and use the measurement tools at that time to observe things, and then the next thing is to interpret this and to think, okay, do I understand what's going on? And in a way, AI or machine learning is yet another tool which can help us in making observations. And I'm very happy with your closing statement where you said, we do not only need artificial intelligence, but we also need human intelligence, because of course AI has a lot of power, but I wonder if it's really able to ever going to, let's say, in an unsupervised way, teach us new physics. I think we will need human beings to do the interpretation and to also think, let's say, in a different way, to come up with new thoughts. Because some people tell me AI is an abbreviation, and of course it means artificial intelligence, but it could also mean advanced interpolation.
Right.
And if you do advanced interpolation, the only thing you can find is things which are in between your points, but you can never let's say extrapolate. Of course, you did say a little bit about it, but I think it's extrapolating is always tricky, and with AI it's probably also still tricky. So we need a lot of human intelligence. So, but thanks a lot for the presentation. Let me have a quick look. If we have any other questions in the chat. Now, I think we covered all the questions. So if there's still somebody in the audience who would like to ask something, take your chance. We are here now. No, it doesn't look like it. Well, then, thanks very much to both our speakers for the very interesting talks, and also thanks for the audience for asking all the interesting questions. I think Professor Jiao Yun, you will probably share the slides on the website of the forum.
Yes.
So if you want to look some details back later on, you can find it there. So thank you all for being here, and look forward to seeing you back at the next session. Is there anything you would still like to say, Professor Yun?
David,
Oh.
would you mind share your today's the video to this other people, and we like to open it on the website, and most other let many more people to start your presentation today. Yeah.
Okay, I will work with you to figure out the logistics.
Yes, thank you very much. Yeah.
Yep. Okay.
It's, today's your work will be, shall be more people to study it and, cite your papers in the futures.
Okay, I hope
Thank you
more
very
people
much.
just would be interested in spring transition, like Professor Finoteno and I, right? We really want the group to focus more on this area as well.
Yeah. Thank you very much for Professor Gulinda Fulanto and Professor David Huang for today's excellent presentation. And thanks a lot for Professor Lear Steen to chair today's meeting. Yeah, we may see you later in the future. Yeah. Thank you very much.
Thank
See you
you.
around the
Thank
corner.
you.
Bye-bye.
Bye. Thank you. Thanks
Thank you
for
very
bye-bye.
much.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.